So practice exam, first couple are easy type things. Again, the biggest key here with these ones is dividing it down the middle and then ranking things on each side. Make sure you're not doing red, white, and blue. And if things are the same, then we don't have to worry about ranking them. So in this case, they're exactly the same, so it's neither. This one, divide down the middle. O or N versus O. O has a higher atomic number. N versus O also has a higher atomic number. They're on Z same side, so Z. This one, two parts. Do I do the ring flip, right? So the bromines equatorial and up, fluorines axial and up, chlorines equatorial and down, and H2 is equatorial or axial and down. So up and down never change. You do the ring flip. Something's up, it stays up, but it just switches from axial to equatorial or vice versa. So bromine up goes axial up, fluorine equatorial up, chlorine axial down, NH2 equatorial down. And then what's the best leaving group? The larger things will be more stable, more polarizable, so that's going to be the better leaving group there. For these ones, constitutional isomers, enantiomers, diastereomers are identical. These two are identical. They're not enantiomers because there is no asymmetric center here. So this carbon is bonded to only three different things. They're two H's, so they're actually identical. They're not isomers that way. These are diastereomers because they have one different and at least one the same, or at least one different and more the same. So these are diastereomers, and these are constitutional isomers because they have the same molecular formula, same number of carbons, hydrogens, oxygens, but different bonding constitutions. Label the chiral centers on the cholesterol medication lovastatin. Again, the best way to approach these, I think, is to find the carbons or the atoms that have either one hydrogen or zero hydrogens on them, right? But they have to be sp3 hybridized, right? So they have to be sp3 hybridized and bonded to four different things. So, right, carbons that have one hydrogen, there's an asymmetric center. 2, 3, 4, 5, 6, 7, 8. Right? Carbons that have one hydrogen or no hydrogens are good places to look at first. So there's 8 there. Remember, it has to be sp3, so any of these sp2s don't work. So for this one, make sure in all these things you read the instructions really carefully. Right? Read the instructions really carefully. So ask what type of reaction you have here and what mechanism with curved arrows. Now I'm giving you the product. That should really help you narrow it down, right, between E1, E2, SN1, and SN2. If I give you this product, you should already eliminate E1 and E2 because this is an elimination product. So it's either SN1 or SN2. And if you see H+, you should automatically know it's SN1, right? SN2 likes things that are reactive, but they have to have a negative charge for reactive, right? The nucleophile is a negative charge. So in this case, again, so now you know it's SN1. I always take a step back. What do you know about SN1? Right? You want to form a carbocation. You got to worry about rearrangements. It's more than one step, right? You might need to do protonation. The solvent's usually involved, right? That solvolysis reaction. If you see H+, use it first, right? It's going to make this into a better leaving group. So you protonate, right? Step 1 is proton transfer. Step 2 is leaving group leaves. Solvent adds. Deprotonation to regenerate the catalyst. It has to be the last step there. So for this one, I want you to draw and label all the beta hydrogens in the molecule and give all possible elimination products. So this is very similar to what we did on a workshop. It's actually the same type of problem. First thing you need to do, though, is identify the carbon that has a leaving group attached to it, because the beta hydrogens are 2 bonds away, right? Beta hydrogens are 1, 2 bonds away, 1, 2 bonds away. So here I've identified there's 5 of them, but there's 2 different types. So there's 2 different types, that means there's 2 different products. I didn't ask for the mechanism here. So this whole thing is the leaving group. It's a good leaving group because it will have a minus charge to be able to do resonance. So what can happen, one of these beta H's can leave. We'll make a pi bond here between these 2 atoms. And you could also make another pi bond here between these two atoms, right? So I wanted all possible products. So each type of hydrogen, each type of beta hydrogen leads to a different alkene elimination product. All right, resonance. Draw two different resonance structures below, including arrows. Circle the most stable and explain your reasoning. So the first thing I would have made you do, if I was going to rewrite this question, I would have said, draw this structure, the structure I'd give it to you twice and say, right, draw one like this, and then see how I redrew it down here? Sometimes that's a good way to do it. So I show the electrons from the lone pair going there, making that pi bond. I show the pi bond resonance, making the plus charge there. So those are the two things, arrows. And then this one is the best one because this is lone pair resonance, and everything in this resonance structure has a full octet. Sorry, say it again. So things you remember. If you're given the products, make sure that'll help you clue in things. If I tell you the reaction type, make sure you pay attention to that too, right? If I tell you here this is an E2 reaction, what do you know about E2s? One step, 3 arrows. The hydrogen and the leaving group need to be antiperiplanar, 180 degrees apart. If they're in a chair, the hydrogen and the leaving group need to both be axial on opposite sides of the ring. So here you don't even need to do anything. It's already set up that way. So you could already draw it. So I told you it was E2, so that's what you know before you even start. Axial E2, boom, boom, make the pi bond, 2 possible products. Or the two products drawn 2 different ways. Same product. Either way is fine. Here, SN2, right? So what do you know about SN2? 1 step, 2 arrows, right? It's going to come from the opposite side, inversion, 180 degrees away. So in this one, this bromine is pointed up and axial. So for the nucleophile is going to come from 180 degrees away. It's going to end up on the bottom side of the ring. And if it's going to be the bottom pointed down, and that carbon has to be equatorial. So that's the big thing people kind of missed there, was whether this was axial or equatorial. It has to be equatorial and down. The lead group's up. When the nucleophile comes, it has to be down, or vice versa. All right, Newman projection. So show the Newman projection for the molecule below. Necessary bond rotation and the products for an E2 reaction, right? So be careful. I told you it was an E2. Mechanisms arrows not required. All right. First, you got to be able to draw this, right? Doing the old-fashioned eyeball-looking guy at the thing, right? Got to be able to do that. We've done Newman projections before, so hopefully that's something we can still do. So this is an eclipse conformation. We're going to need to get into a staggered conformation because we need to get the bromine on 1 carbon, on carbon 2, and the hydrogen on carbon 1, 180 degrees apart. So what I did, I didn't rotate. It looks like I kept 1 the same, and I rotated 2. 60 degrees to the left, counterclockwise. That got these things lined up. So those are 2 things we want to eliminate. Notice what this helps you see, though, is that this ethyl and the O-methoxy will end up on the same side of the pi bond, right? So the pi bond, you can't do rotations about the pi bond. So these 2 will have to be on the same side. And this H and this methyl will also have to be on the same side. So just to emphasize this again, you get these 2 things lined up, and then whatever's on the same side will be on the same side of the pi bond. Right? That's a nice way to make sure you get the things lined up correctly. Bromine's on 1 carbon, the leaving group's on 1 carbon, hydrogen's on another. Hopefully you practice this quite a bit as well. Label the solvents below with protic or aprotic. Simple as seeing, can you recognize OHs, NHs, SHs, and PHs? So if it doesn't have that, it's aprotic, it's protic, aprotic, aprotic, protic. So I'm trying to overthink those ones too much. All right, so multiple choice questions. So for this one, circle the molecule that will undergo an elimination reaction. So again, for elimination reactions, you need what? So E1 or E2, what do they have in common? They both need beta hydrogens. Right? So if you look at these, only one of these molecules even has beta hydrogens. So that's really what I was trying to get at when I was asking this question. So if you look at this carbon, right? Sigma, how many hydrogens are 2 bonds away? There's none here, none there. This carbon, there's just hydrogens. There is nothing 2 bonds away. From this carbon, there's no hydrogens there. From this carbon, there is hydrogen. So only this one will actually undergo an elimination reaction. This one, what type of reaction? So people might ask, well, how am I supposed to know that? Well, if you look, you're given the products. So you should be able to automatically eliminate, right, what? E2 and E1 because there is no pi bond. So this is between SN2 and SN1. And then you look at the type of nucleophile, right? And or you look at the electrophile, it's a secondary, so it could be everybody. You look at the product, no elimination, so it's SN1 or SN2. You look at the solvent or nucleophile, and you see it's not reactive, there's no minus charge, so it must be SN1. You also could look and say, well, the leaving group's on this carbon, but now the thing that adds is on a different carbon. That tells you there's a rearrangement. There's only rearrangements when you have a carbocation, and you only have carbocations when you have SN1 and E1. So it's like a process of elimination there. You can figure that out. The enantiomer for this molecule, right, again, everything just needs to be the opposite, right? Everything needs to be opposite. So if this OH is hatched, it needs to be wedged. This is wedged, it needs to be hatched. So that's the correct answer. This is just the same thing. This is a diastereomer, and this is a diastereomer too. Rate stuff, what reaction doubles with the concentration of the nucleophile and inversion happens? So double, you hopefully know that one at this point. That's an SN2. Right, that's an SN2. So this is kind of a reverse of a previous question. So instead of giving you the reaction type, I give you the reaction products. Give the mechanism arrows for the second reaction, and it's inorganic byproduct, right? So inorganic means without carbon. So HI or H plus I minus would work here. So this first one, how do you know what kind of reaction is? Well, I look at the product, so I know it's an elimination. Then I look at the alkyl halide and a secondary, so that doesn't help. And then I look at the reactivity of the base or nucleophile, and it doesn't look reactive. It doesn't have a minus charge, so I'm thinking E1. E1, the first step, maybe I lost it here. Oh, the first step is the same as here. The leaving group leaves. Let's see if I have it down here. I can draw it in here quick. Leaving group leaves. Look for the beta hydrogens. You worry about making carbocations, so you're worried about can I do any rearrangements? This is secondary benzylic, so it's pretty stable. So I'm going to do an elimination. And that leads us to the products right there. And you also make, let's see, OH. So there was an I minus here still. So this H could fall off, and that gets us H plus I minus, which is the same as HI bonded. There's the E1 version. This one's SN1. How do I know that? Again, non-reactive solvent base. Leaving group leaves. Solvent adds this time. Instead of taking the beta hydrogen, it adds. Deprotonation, or the H just falls off. Gets us there and gets us the final product. So what do you need to know about free energy diagrams? The major thing we talked about are kinetic and thermodynamics. So a kinetic product is the one that comes from the lowest energy hill. A thermodynamic product is the most stable product. So what I'm asking for is product X is both kinetic and thermodynamic product. Draw a free energy diagram for below, including both products. So I'm looking back up here, right? X and Y. So this reaction can have two products. And I said X is both the kinetic and thermodynamic product. So if I tell you it's the thermodynamic product, that means you know X needs to be lower in energy than Y. So don't worry about where it is in relation to the starting material. I don't care at this point. But you need to know X is lower in energy than Y because it's thermodynamic. You also need to know that X came from a lower activation energy hill than Y. Right? You could have gotten fancy with this. You didn't have to. All I wanted was to show that you knew basically definitions of thermodynamics and kinetics. All right, last one was just mechanism resonance stuff, a little rearrangement type thing. So I gave you the products and asked for the arrows. One part was confusing for folks that this is exactly the same as this. And then I asked for the rate determining step. So first step, leaving group leaves. You do ring expansion, so rearrangement, hydrogen shifts, same here. Lone pair resonance. This would be the most stable structure too. And the slow step, the rate determining step, is when you form the carbocation. So that would be this, right? Because you're no longer have a full octet.